So this talk appears under three headers. So first of all, of course, we're in these wonderful facilities of the International Center of Mathematical Sciences, who are kind enough to host us here. So thank you very much for that. It's also part of the conference on the mathematics of random systems that we've been running here as part of the doctoral training center of the same name. So in the last days, we've been hearing talks from the final year students in the context of analysis, modeling, and computation of random systems. And finally, this is also streamed as part of the World Online series on machine learning and finance. So all this audience is befitting to the distinguished speaker today. So this brings me to Des Higham, who's renowned for his contributions in numerical analysis, specifically also to stochastic simulation, partly with applications in mathematical biology. He's done groundbreaking work in network science and recently also in the area of data science. I was a fellow of the Royal Society of Edinburgh, and more recently has also been awarded the Shepherd Prize from the London Mathematical Society for his work that has an intuitive component, he says, and that is also explainable to a more general audience of non-graduate mathematicians. So who could be better placed to talk to us about deep learning and what could go wrong? So thanks very much, Des, for the talks.
Well, it's a great pleasure to be here, and this is a topic I love talking about. So let's get ahead. This is the International Center for Mathematical Sciences. So I'm talking about the maths aspect of this topic, but it's a public lecture, so I'm trying to keep things as accessible as possible. And feel free to chip in with questions, especially if you're here in the audience, to try and break the monotony. But there'll also be questions at the end. Fire if you like. So I'm talking about AI. We're all aware of the fantastic breakthroughs that AI has had, lots of success stories. There are also issues that people are clearly concerned about these days. I've listed a few of them there. I'll touch upon these issues perhaps in a tangential way, but I'm sure you're all aware of some of the debates going on around the use of AI. That also leads to the idea of regulation. Should we be making laws about how AI can be used? What kind of safeguards should be made around the use of AI? And I'll also say a little bit about how maths and stats might impinge on that. But I really want to talk about a more mathematical topic, and that's really vulnerability. So do these systems work? What are they vulnerable to in general? I'm going to focus on what I know about a little bit myself, which is image classification and the use of deep learning tools. But some of the concepts I mentioned are more general. And of course, nothing is perfect. No system is perfect, and human beings are not perfect either. So the types of vulnerabilities I'm going to talk about are, in a sense, analogous to things like blind spots and hallucinations and optical illusions. So in a sense, it's the machine equivalent of those kinds of weaknesses that we're looking at in this talk. I'm not going to give any technical description of what deep learning is. There's a picture there that might help you appreciate some of the basic pipeline, the sausage machine pipeline that goes in. So we start off on the left with some data. In this case, it's going to be an image. So there might be red, green, and blue components to the image. So those are lists of pixels and their locations. That input gets passed through various mathematical operations called layers, and then it gets output at the end. And if we try to classify the image, the output will be perhaps a single answer. This is a dog, or it might be a probability associated with each possible class. So it might be 0.99 dog and 001 cat. So you may well choose to classify according to the most likely of those outlets. So that's the general idea. It's a tool, a black box that classifies images. And in the deep learning context, there was a big breakthrough around 10 years ago when AlexNet won a competition, significantly outperforming state-of-the-art tools. And the big surprise was that this deep learning approach involved lots and lots of parameters. So you had to tune 60 million numbers to get this to work. So if you think of little dials on your black box, there were 60 million dials. You had to get them all in more or less the right position to make this thing work. It's a hugely expensive computation to make, but it did do surprisingly well in this competition. Since then, there have been lots of similar tools developed, but they do tend to have extremely large numbers of parameters. So that itself is something that's worth thinking about in terms of the resources that are used to train these tools, and also things that might go wrong with them. Okay, so we'll maybe come back to that later. So here's the kind of thing I want to discuss. On the left is an example of what I'm sure we would agree is a photograph of a American school bus. These authors here decided to add a little bit to that image. So what in the middle there is a pattern of pixels that was chosen by those authors. A small amount of that pattern of pixels was added to give us the image on the right, which, as far as we're concerned, I think is the same image. This is imperceptible to the human eye perturbation, but this very sophisticated tool now decides, rather than being a school bus, the perturbed image is now an ostrich. So we've managed to change the classification with a tiny perturbation, tiny change, which to us is imperceptible. Okay, that might be intriguing. The title says it's an intriguing property. It might be disconcerting, depending how you think about it. There are clearly issues here around security and defense, and possibly legal issues if you think of these types of attacks being used in practice. So this would be called an adversarial attack, because there's an adversary. There's somebody trying to make things go wrong. This is not a random perturbation, so you can't just choose that set of pixels in the middle at random. If you try that, typically it doesn't work. This is a very specially chosen perturbation. So optimization has been used. It might be surprising that you can do this. This is not a special case. You can typically do this with more or less any starting image. One way to think about it is that there are lots of possible patterns you can choose from in the middle there. In a sense, it's a very high dimensional problem that we're solving. All the pixels there, if you put them in a big line, there'd be loads of possible pixels. Each one, you can choose what value to assign that pixel, red, green, blue. So there's so many different directions. Maybe it's not so surprising that at least one of those directions is going to cause this classification tool to make a new classification. Okay. So we'll get back to that a bit later, how you might analyze that a bit more mathematically. There's another early paper there that's also worth reading for anybody who's got any interest in this topic and hasn't read about it yet. So these papers are full of good ideas. They're very easy to read and do raise this issue of susceptibility to attack. And that generated a whole slew of research, even carrying on to this day. Designing attacks. So what's a good way to perturb an image to cause a misclassification, or at least a different classification? There are corresponding defense strategies. So for example, an obvious one would be when you're training the network, when you're teaching it through example, give it the example on the right and make sure it knows the example on the right is still a school bus. So give it the adversarially attacked images with the correct labels, and maybe that will help to guard against these types of attacks. And that works to some extent, but it's by no means perfect as a defense strategy. There's lots of variations of these types of attacks. A targeted attack would be the case where we wanted to make that school bus become an ostrich. So we chose ostrich as our new class. Untargeted is the case where we don't care what the new class is, we just want to change into any new class. That would be an individual attack there because we just attacked one image, but you can look for a perturbation which works on a whole range of images. And in practice, the same perturbation can be successful at changing the class on a whole range of images. And you can also attack universally in the sense of these deep learning networks. So the type of perturbation that works for one of these networks will often also be successful on similar networks, even with different architectures. You can talk about black box attacks. So a black box means the person who creates the attack only has access to the system. They can give it an input and they can get an output, but they don't know what's inside. A grey box attack might be when the person attacking has a bit more knowledge, maybe knows the parameters in the system or something about the architecture. White box might mean they have access to some of the numbers inside the black box, in particular the gradients, telling you how sensitive some of these components are to perturbations. Open box is something I invented myself as a name. This is the extreme case where you can actually go in there and change the code. And I'll say a little bit about why that might be relevant towards the end. But there's lots of ways that you can play around with these ideas, be creative about attacking these systems. So I'll spend a little bit of time showing you examples, and then later on we'll say a little bit more about the maths and the stats that might go into analyzing these circumstances. So here's an example I came across via my Twitter account. So these are called adversarial patches. So this is a physical object you print out on a piece of paper, a carefully chosen pattern. And if you put that around your neck and wear it, then the video surveillance system no longer recognizes you as being a human being. Okay, so the person on the left is not wearing one of these patches, so they're recognized by this video surveillance system, and the person on the right is wearing a patch, so they're not recognized. And imagine if you're trying to rob a bank, this might be quite a handy thing to put on before you go through security. And of course, this is not supposed to be imperceptible. Human beings can look at that and say, that guy's got something suspicious about him. These attacks are designed simply to fool the automated version of the system. They're not trying to be imperceptible to humans. This is some work that I'm doing with my student, Lucas Behrens. We focused on this idea of printed or handwritten digits or text. And in this case, there's a very famous data set called MNIST, where a bunch of, I think, Royal Mail workers were asked to handwrite digits. And you can train a system to recognize digits from 0, 1, 2, 3 up to 9. It's very simple these days to generate tools that can recognize to high accuracy those digits. So here on the left is an example from that data set, which I think we would agree is a 7. In the middle is an attacked version of that 7 using a technique called deep fool. Deep fool is built into one of these tools, PyTorch. It's a standard adversarial attack technique, and it gives us the image in the middle, which is now classified as an 8 by the system. Now, that's a small perturbation in a sense, and in a very well-defined mathematical way, it's the smallest perturbation you can make to the picture in terms of changing the individual pixels. But you might argue that there's not a very good example because the background has been smudged. So you might be suspicious that something has happened there. So with Lucas, we looked at this idea of, rather than perturbing everything, look at what we call a component-wise perturbation. In this case, it would correspond to only perturbing the non-zero pixels or the non-white pixels. So don't change the background, only change the non-zero pixels in the image. And we have the perturbation on the right, which is still classified as an 8. So it's a misclassification where we've only changed the non-zero pixels in the image. And again, you can do this generally on a typical data set from MNIST. Okay, and we think that's reasonable. You might look at that and think, well, the ink isn't very good, or the paper's a bit smudgy. It is not as noticeable as the one in the middle in some sense. And if you think of writing checks or putting dates on documents or signing documents, the idea that you can have something that a human being recognizes as one thing and yet the computer recognizes as something completely different is clearly an issue in various applications. Okay, so even though MNIST is really regarded as a very simplistic data set, it does have this feature to it that the standard perturbations, you could argue, are noticeable, but if you do something else, then you can make something a bit more heavily disguised. And here's the example which was referred to in the image that goes along with this talk. This is a very well-known piece of work. These authors looked at road signs and showed that you can make fairly small, in the sense of, little bits of sticky tape on the road sign changes, and that can completely change the classification that's used by a standard automated driving system. So you can take a stop sign, add a little bit of black and white stickerage on it, and it will now interpret that as a 45-mile-per-hour speed limit. So that's clearly something of concern. And it works at various angles. It's not just a one-off perturbation. That is sort of general in the sense that it does work over as the car is approaching the sign. This doesn't really fit in with the talk, but I couldn't resist mentioning it because the title looks as though it does. It's called Natural Adversarial Examples. But on the top there, these are just images which are misclassified. So there's nothing adversarial in the sense that nothing's been perturbed. They just found images which are hard for these systems to classify. And you can sort of see why. On the left, that's a broken piece of rope, but you could argue it's a little bit like two jellyfish and so on. So these are, in a sense, almost optical illusions or somewhat ambiguous images. If you go back to MNIST, people that have worked with this will know that some of the MNIST images are, again, somewhat ambiguous. Just because a person has been asked to write the digit 3, it doesn't mean that what they've written really is a digit 3. If the rest of the people in the room think it looks more like a 5, but they think they've written a 3, then what is the correct label? So there's always some ambiguity in the labeling process that's worth thinking about. It's interesting to see how they found these examples. How did they crawl the internet? By using graduate students. We asked a bunch of students just to look for examples, real examples where things go wrong. But the paper does have another idea where you simply change the color, at least some of the color in the picture. So here, for the blue and the red versions, the system identifies a dragonfly, but for the yellow version, the system says that's a banana. And I think it's actually the handle of a gardening tool. So playing around with the colors can be enough to cause a different classification. Okay. Here's another whole genre of attacks. These are physical attacks on the computer itself. So these are laser beams being fired at the computer. So you try and change the bits being stored on the computer by firing a laser beam at it. And that's something that has come out of the cybersecurity world. And so there are papers on that. Another thing you can do is if you have access to nearby memory locations, if you constantly flip the bits, then the nearby memory locations that you can't access will be affected due to some sort of physical interaction. So by flipping bits nearby, you get to possibly change the parameters in the model. So this has been looked at quite seriously in a more engineering context. It's very much a heuristic approach. You can't have any control really over what you're doing, but it can cause effects on the classification results. One of the issues that's discussed around AI is explainability. So it's one thing to have a system that works. If you're using that system to make decisions, especially about human beings, you should, in principle, be able to explain how that decision was reached. So can we explain why the AI tool is doing what it's doing? You might say, well, here's all the 60 million parameters. That's the model. Work through the mathematics, and you'll find out that you don't qualify for this insurance. But that's not really explaining. In the context of images, there is some work where people develop algorithms that try to explain the result. So on the left, there's a picture of the dog, and below that, this is the explanation of why it's a dog. So it's got floppy ears, it's got big eyes and a big wet nose and a little tail. That's why it's a dog. If you think about these adversarial attacks, you could make a tiny perturbation to that image, and it would be a cat or a chicken or a toaster. And it would be a chicken because it's got floppy ears, big eyes, and a wet nose. It would still be the same explanation, but it would be the wrong answer. So clearly, explainability has the same vulnerabilities as the basic classification process. Now, these authors went a bit further, and they actually attacked the explainability algorithm. And it turns out you can make the explanation into anything you want. So you can make any pixels light up to be the explanation of why this has been classified as a dog. Okay, so they chose to make the pixels light up to make this text. I think they missed a trick. I would have said meow or I'm a cat. Give me a bone or something, but that's what they chose to have as the explanation. So, you know, these tools might be useful, but they're certainly suffering from the same types of vulnerabilities as the underlying classification tools. Here's the variation on an adversarial patch. Now, these are adversarial spectacles. So you can print these out and put them on. And if you're not famous, you can become famous. And if you are famous, then you can become not famous. So this causes misclassification. Again, it's not really a small perturbation, but you might argue it might not be noticed depending on where you were wearing the spectacles. And I should say, I'm actually wearing an adversarial shirt. Computer thinks I'm Nicola Sturgeon. He's doing the same thing. Alain is also. So these are available, Marks and Spencer's. And you can imagine the impact that might have on facial recognition usage. The London Met, apparently, according to a recent Guardian article, are still considering the use of facial recognition to scan through a crowd and see who's there. But if you can wear a pair of spectacles and change your identity, that casts some doubt on the use of this system, I think. Okay, and that leads us a little bit into regulation, which I'll spend a couple of minutes on. There's something called the EU AI Act. So this is the European proposed set of regulations around the use of AI. There's a document you can look up. I picked out there, number 2 is telling you what you should be doing. And of course, this is not relevant to us directly in the UK, but if you're selling anything into Europe, and this will be relevant, these will be the rules you have to follow. So these are some of the practices that you should follow. It doesn't really say that the software should work properly, not explicitly. It does talk about possible biases or shortcomings that you should be aware of in your AI system. So they haven't really, in my opinion, nailed down this type of vulnerability. One thing they have done is talk about levels of risk. So they talk about high-risk applications, which are things involving humans or loss of life or huge financial transactions. So they want to impose these regulations on the use of AI in high-risk environments. So I have an app on my phone which uses a neural network to tell me to identify birds based on the bird song. And I don't think it really matters whether they get it wrong in that context. But if you're trying to guide a car around the city, I think that's a much more relevant example of a high-risk application. Also, when I was reading this, they referred to AI and they said Annex 1 gives a definition of AI. So the people that wrote this European proposal tried to define AI, and they didn't do a very good job, in my opinion. They gave a list of things, A, B, C, and C is statistical approaches, Bayesian estimation, search, and optimization methods. So if you're a statistician or an optimizer, you're doing AI, and you might be subject to these European laws. That's what they seem to be saying. So clinical trials using standard methodologies suddenly have to undergo these regulations. That's one interpretation of what they're saying here. And yesterday I attended online an Alan Turing Institute's workshop on the EU AI Act. And they mentioned it's going to take a long time. Even if it goes through, it will be around 2025 before it goes through. But there may be a delay because since they started writing the document, things like ChatGPT have come around. So some of these issues are suddenly a lot more serious, and there's some possible concerns are missing from the document. In particular, they talk about foundation models, which can then be used within lots of different applications. So if you've written a foundation model, you don't know whether it's going to be used in a high risk or a low risk application. Should you be responsible, or should the person further down the pipeline be responsible for any flaws in that foundation model? So those are the kinds of issues that were discussed yesterday. And the UK government got involved in a similar process. The first thing they tried was a white paper looking at what they called a pro-innovation approach. So they were trying to be as hands-off as possible, trying to encourage development and innovation. But even then, they had to make some sort of, had to show some sort of concern. So they said, please make sure that your AI is used safely, technically secure, functions as designed, and is transparent, explainable. And I think the maths, in a sense, proves that you can't do that. So there might be a law coming out which mathematically doesn't make any sense. However, that was last year, and then in The Guardian, just recently, I came across this article which says the government is now considering a different approach to AI regulation, which is even more hands-off. They're just letting existing regulators deal with AI within their sector. So the idea that they're proposing now is the Health and Safety Executive and the Human Rights Commission and so on, they'll have to deal with AI in their own little silos individually, which you know, again has its own possible issues. Okay, so that was a bit of background, some of the ideas that are being used. I want to spend a little bit of time now talking about some of the maths and the stats that goes in to some of these ideas. So the design of those attack algorithms really is based on maths. So you're looking at the worst possible thing to do to the system. So if you prod it in a certain direction, what happens and what's the worst possible direction in which to prod this system to make it go wrong? So that's optimization using calculus. You know, calculus tells you how things change. If you make a small change to the input, what happens to the output? So it's traditional maths, and linear algebra is everywhere. These are big systems. You get what are called matrices coming out, which are large. Now, those are the ingredients that tend to go in to these algorithms. But we can also take a step back. And there's this war of attrition going on between attack and defense. Can we say anything about what's going to happen? Is there ever going to be a perfect defense? Is there always going to be a way to attack these systems? So these are the bigger picture questions we can look at. To answer those questions, we have to make assumptions, but we love making assumptions in my world. So make some assumptions and prove something and see what happens. Okay, so are there some conditions, some assumptions we can make which tells us perhaps that it's always likely that a successful attack will exist? If it exists, is there an algorithm which will compute that attack? If there's a trade-off between having an accurate system that classifies accurately on a big data set, but is robust to vulnerability, then what is that trade-off? Can you find a compromise system which is fairly accurate and not susceptible to these attacks? So those are the kinds of questions we can certainly address if we're prepared to set up the appropriate mathematical framework and make some assumptions. So I don't have the time, or it wouldn't be appropriate to go into all the details, but the kinds of things you have to think about if you're going to prove results are what's the input dimension? So that would be how many pixels are there to play with in the input. What type of training data do you have? You know, how many pieces of training data are they from a certain, what we call distribution, from some population? What kind of test data are you going to then look at? What kind of architecture, what structure in that sausage machine are you going to set up? And it's also important to decide what is small and what is large. And in infinite dimensions, that's not such an easy question. So we would say, what kind of norm are you using in the mathematical sense? Or if you go back to the number 7 picture, there are clearly different ways of measuring perturbations. The one in the middle is a small perturbation in one sense, and the one on the right is a small perturbation in another sense. And the answers that you get can be very different when you ask these questions and use different ways of measuring size. Okay, so here's a little bit of maths. There are people here that know a lot more about this world than I do, but this is really to try and set up the kinds of things that can be proved. And this is to do with large dimension what happens in large dimension when you have lots of inputs, lots of numbers that go into the input, lots of pixels in the image. We're going to look at what's called a unit sphere. So in 3D, I think we're all happy with the idea of a unit sphere. It's just a beach ball. And unit means the radius of the sphere is 1. And then we can talk about a spherical cap on the sphere. So here, if you think of a North Pole, you can choose any North Pole you like, then you rotate the sphere so that the North Pole is at the top. And you're allowed to choose an angle, theta. And you can look at all the points on the sphere which make an angle no more than theta with the North Pole. So that's like a little hat sitting on top of the sphere. That's a spherical cap. Okay. Now, what's completely amazing, and it's impossible, in my opinion, to understand intuitively, and certainly to visualize, is what happens when you go to more than 3 dimensions. So here we've got 3 axes, think of x1, x2, and x3. If you had x1, x2, x3 up to xn, and let n be a large number, so you have n pixels in the image, for example, you can still talk about a unit sphere. It's all the points which are distance 1 from the origin. But it turns out, once you've chosen the North Pole, most of the points in the unit sphere, most of the area in that unit sphere is around the corresponding equator, which is a very difficult thing to get your head around. But it's true that once you've chosen the North Pole, in large dimension, most of the area of this unit sphere is around the corresponding equator. Another way of saying that is that the spherical cap, as long as theta is not 90 degrees, the spherical cap is an exponentially small area, has an exponentially small area compared to the whole sphere. So spherical caps are tiny. You can fit exponentially many of them onto a unit sphere in high dimension. Okay, so that's one of the ingredients that can go into these types of proofs about the inevitability of attacks. So I've given a reference there. This is, it's not a well-known phenomenon, at least from my world, but it is standard calculus. Standard integration theory allows you to look at these areas and prove these results. So in a sense, it's elementary mathematics, but it's completely counterintuitive. There's a quote here from Vera Kukova: mathematics alone guides us in this world where the senses can't reach. Okay, so it's difficult to visualize or appreciate these results, but you can do the maths and it works out. So why might this be relevant? Let's think of the simplest possible case of classification where there are 2 classes, so cats and dogs, and think of the beach ball, the unit sphere, but think of it in n dimensions if you can. We want to split that beach ball. The images lie on the surface, and we have to classify images. So we have to split that beach ball into 2 regions, 1 region for cats, 1 for dogs. And in high dimension, we have to choose roughly half of the sphere for each of those classes. Otherwise, one of them has a tiny spherical cap. And that's a degenerate case where almost nothing is called a cat. So we want to avoid those degenerate cases. So any sensible classification more or less has to put what we call the boundary, the decision boundary, or the place where you change over along some sort of horizontal chop through an equator. But once you've done that, we know that in high dimension, once you've chosen your North Pole, most of the points lie near the equator. So a randomly chosen image will be near a decision boundary. So that's the essence of what goes wrong. This is a very contrived example, but we can generalize that quite nicely. We can map things smoothly into more general classification problems. So that's one way to understand why things might go wrong. The randomly chosen image, at least under appropriate assumptions, in high dimension is very likely to be close to a decision boundary. Okay. One of the nice things about this type of analysis is that we don't have to commit ourselves to what is the ground truth. You can define an adversarial attack as a perturbation that changes the classification. We don't have to say which of those, if any, if either is the correct classification. You just have to say a small perturbation changes the classification. And the kind of games that we're playing here arise because you can give me epsilon and you can decide how small you want the perturbation to be. So you give me epsilon telling me how small that perturbation is. I'm then allowed to choose n, which is the dimension of the input space. So for any epsilon that you give me, no matter how small it is, I can choose dimension big enough so that it's very likely that a random point can be close to the boundary. So those are the kinds of results that we can prove in this setting. So here's some examples if anybody wants to follow this up. One of the earlier papers I came across was that first one there from 2019. So under appropriate conditions, these nasty examples where you can make small perturbations and change the class will occur, and they're very likely to occur. So the probability of an adversarial example existing is close to 1. And that's been extended by various authors. There's also this robustness accuracy trade-off. And if you let mathematicians choose the data that you train on, then things can be absolutely terrible. So if you let us choose the images, then we can make things be as bad as you like. Now, there are examples that when I say sensible training data, I mean we haven't cheated and we haven't put a cat right next to a dog with a very small space between them. That would be naturally a difficult thing to classify. So these are sensible in the sense that the classes are well separated in some sense. So it's a reasonable game to play. But even so, we can come up with a data set which defeats the network in the sense that the network can't be accurate and stable. So if it wants to reproduce the training data accurately, it therefore has to be unstable, has to be susceptible to perturbations. This is in the deep learning context. And so that's sort of worrying, but it does require us to be able to choose the data that we train on. So in the sense, it's quite a contrived example, but it just goes to show that you can't really have a law that says you must be able to show that your network is always going to do the right thing, because we can find data which messes things up. So that's just the way maths is.
Sorry, just a quick question on that last point. You sort of the way you stated your theorem is effectively for epsilon, you can choose a dimension.
Yes.
It's, if we're assuming floating point data, which there's a fixed resolution, is there any expectation that you could find, for a fixed dimension, you could come up with a network which the required epsilon would have to be less than the resolution of your data?
I think that depends on the setting, of course. I'll say a little bit more on a couple of slides that might help that. But in practice, you can do this. In practice, people are computing these examples. So in that sense, these are not completely unrealistic, I would say. Okay. So as I said, that in the beginning, we use calculus and optimization to find these attacks, and they tend to correspond to the ones that are used in this theory. So it is not surprising that you need to have that information if you want to make these attacks. So if it's a black box that you can't interrogate, it is going to be tricky to do these attacks. However, you can do what's called finite differences. So if you have lots of access to inputs and outputs, you can approximate gradients and you can build up things like Jacobians, we call them, and you can simulate these attacks quite nicely without knowing what's inside the box. But in practice, you are trying to approximate something that's going on inside. As I said earlier, and you can prove theoretically that random attacks don't work for these theorems. So you have to know what direction to perturb in. You can't just randomly change the pixels by a small amount. That won't work in these settings. So they're robust in that sense. Okay, so the final topic I wanted to mention was what happens if we're allowed to go inside and play with the parameters in the network, which might sound a bit crazy, but I'll try and justify that shortly. So we can actually recode the software. I'll give a couple of intuitive reasons why that might be a successful thing to do if you're changing parameters in the network. So here's one idea called network pruning. So the picture there is meant to just emphasize there's lots of parameters, lots of components in this system which have numbers attached to them. And we can potentially, when you train the network, you're putting numbers in. Something called the lottery ticket hypothesis says that in any big network, hiding inside there is a much smaller network that can do the same job. So in a well-defined mathematical sense, these 60 million parameter models are not necessary. There'll be a much smaller model with the same kind of structure, which does almost the same job for classification. The trick would be trying to find it, but at least theoretically it exists. So that suggests there's lots of redundancy in this network. Lots of things could be thrown away and you'd still have a very similar tool. That can be made more accurate. So I've quoted a theorem here. Don't worry too much if it doesn't mean anything, but roughly speaking, you can make 99% of that network disappear, and in a well-defined sense, it will still do a good job, at least in some average sense. Okay. The other insight I wanted to mention was what's called separability, linear separability in high dimension. So here we need the concept of a convex hull of points. So the picture there corresponds to 2 dimensions, but think of, this is from Wikipedia, this is a nice idea I came across recently. If you think of pins sticking out towards you, and then you get a rubber band and you put it around, and that rubber band forms a shape. So anything that becomes a vertex of that shape that's been formed, that would be a vertex of the convex hull. The convex hull is the region contained by the elastic band. So some of those points there are vertices. They're the ones that the band is touching, and some of them miss out. They have to stay inside. They don't form vertices of the convex hull. And an important difference between being a vertex and not being a vertex is linear separability. So any of those vertices can be chopped off from the rest by drawing a straight line with a ruler. So maybe I can try. So for this vertex here, there's a straight, whoops, this is not very intuitive. There's a straight line that, I've got no idea how this is working. I'm sorry for those people back home. There's a straight line that cuts off that vertex from the others. Okay, and this generalizes into higher dimension. You can have a convex hull of points in any dimension you like. And you can talk about the vertices. And if there's a vertex of the convex hull, there's what's called a hyperplane, which is a generalization of a straight line, which separates that point from all the rest. Okay. Now, in 3 dimensions, if you put lots of points down, this one in 2 dimensions here, put lots of points down, it's very unlikely that they'll all get this nice property of being a vertex of the convex hull. Some of them are going to get caught inside. What's amazing is that in high dimension, it's very, very likely that even exponentially many points will all be the vertices of the convex hull. Okay, so you can put lots of points down, and say in dimension 100, you can put 3 million points down at random, and with probability greater than 0.99, they'll all be vertices of the convex hull, so they can all be chopped off from the others by what we call a hyperplane. And those neurons that make up the deep learning tool are essentially building hyperplanes. So that gives you some insight into that, the possibility here that these authors had for fixing an AI system. So if you've built a very complicated many neuron AI system, it's working perfectly, and then one day a new piece of data comes along and it goes wrong, then these authors showed how to add 1 extra neuron to the system. So you don't have to do any retraining, just add a new neuron which only fires when it sees that new data point. It will stay silent on everything that's been seen before, but it will only fire when it sees that new data point, and it will therefore cause the output to be correct. So for a small number of errors, you can fix them by simply adding a few neurons to your system because of this linear separability. This exponential amount of data that things work on doesn't get changed, and this 1 extra point that you're concentrating on, you can play around with it and make sure that gets identified appropriately. It was a really clever trick. But then we realized that you can also attack a network with the same idea. So here's the scenario we looked at. You have your network. There's an owner, and the owner has a set of test data that they use to validate their system, and that's kept secret. So nobody else knows what this set of validation data is. And there's an attacker, and the attacker has a particular image, and they want their image to be classified in some way. So they're allowed to go in and change one of the neurons, and they do so, if they're successful, they do so in a way that doesn't change the output on the test data. So here's the test data going through correctly, but on the trigger image, because of this change neuron, they get whatever behavior they wanted. And because of those two insights I gave before, the redundancy means that there are neurons there that don't do anything. So if you change them, they don't affect the behavior on the test system, but they're also separable from the rest. Now, this new data point that you've got, this key is separable from the other data points. So you can use that new neuron that you've fixed to work and fire appropriately on the new data point. Okay, so those two causes allow you to have this kind of effect. And we have some rigorous theory saying this will work with high probability. But why is this relevant? Who's going to go in there and change software? You know, well, a software developer, if you're a member of the team, maybe you're a bit disgruntled or you're being paid or blackmailed into doing it, you could just change one of the neurons with your colleagues not knowing that things have gone wrong. But more importantly, there's a whole movement to democratize AI, because training these networks is incredibly expensive. It's only really available to these high-tech companies that have the appropriate resources. So they're being encouraged to give out their networks, give out their 60 million parameters so the rest of us can play with what they've got. But how do we know that they're giving us 60 million parameters that don't have these kind of things buried inside them? So do you really trust the person who's giving you 60 million parameters that they haven't caused the system to do something specific when they want it to? Okay. You can also outsource the training. So you pay Amazon Cloud to do the training for you. They give you back the numbers. Again, how do you know that they're appropriate? Transfer learning occurs when you take a network and you add maybe an extra layer to change the application field. So again, if you're transferring somebody else's network, maybe they've given you something that isn't quite what you thought it was. So there are issues there, and there's some mathematics saying that these things are vulnerable to these types of perturbations. Okay, so just to wrap up, I tried to put across the idea that maths and stats is used already to do these attack systems. It's basically calculus optimization, linear algebra that reveal these vulnerabilities in practice. But the same type of mathematics plus some other maths and stats, including this high dimensional concentration of measure maths, allows us to look at other questions. So what's the worst case that can happen? Is it inevitable that things will be vulnerable? And what about random attacks? And generally, they're not as significant. They don't cause the same damage. There are issues that I didn't have time to talk about that is of great interest to me. One is whether these attacks can be computed in high dimension in a sort of Turing machine theoretical sense. Are they computable? What would the complexity be in high dimension of finding them? An issue that was sort of mentioned earlier, these AI computations are done at incredibly low floating point precision. That means the number of digits that get carried when the operations are done, when the multiply, add, take away, divide is done on the computer, some of these systems only store 3 digits. So there's a huge error in rounding every one of those operations. You've got 60 million parameters. You're doing lots and lots of software computation, lots and lots of floating point computation, only carrying 3 digits each time you do one of them. So what can you possibly say about the output? What's the rounding error going to be under that level of accuracy? So what we're analyzing in these theorems might be nothing like what's happening in practice. There's such a lot of noise from floating point that maybe we're doing something totally different. Nobody knows maybe what these systems are really doing in that level of low precision. Okay, that's another issue to worry about tonight. And as I said, there are lots of other issues associated with AI. Some of them we've touched upon here. And to deal with these, it's not just maths and stats, of course. There's lots of interdisciplinary work needed to come up with answers around these issues, ethics and privacy. What's the inherent bias in these tools? How do you interpret the answers? How secure are they? How much resource does it take to do the training? Should we be redoing all the training again, or should we just be, being a bit more careful how we use our resources? As we discussed earlier, how do you regulate these tools? What kind of laws would be appropriate? Okay, so I'll finish there. Thanks for your attention.